Okay, so another improper integral. We have integral from 0 to infinity, and we would like to look at how to do this one. So it's type 1 again. However, this one, the actual integral is going to be a little bit more difficult for a couple reasons. First, we have to figure out actually how to integrate this. We do notice that we have here this inner function, but a substitution here won't really help us. So we can actually set up instead to do integration by parts. So let's make a choice for u and for dv. We know, following the Lie hierarchy, okay, that here we have an algebraic function for x, and we have an exponential function for e to the negative 2x. So that's going to be here and here, which means that the algebraic function is going to be our choice of u. Perfect. Let's set it up. We have u is equal to x. dv will be e to the negative 2x dx. And that means that du will just be dx. While over here, v, this is going to require a little bit of a substitution, or you're essentially undoing that chain rule in your head. We're going to get here e to the negative 2x divided by negative 2. Okay, so we've undone that chain rule in our head, and now that we have our IBP set up, we can go and plug it all back in. We also have to deal with the fact that it was improper, so we're going to introduce our parameter t, and we have x e to the negative 2x. We take limit as t approaches infinity. Fine. We leave the limit alone, but now we know how our IBP works out. So we have u times v is negative 1/2 x e to the negative 2x, and then we have minus v du, so that's going to be minus negative 1/2 if we take this constant out right at the start. And then we're going to have here the integral from, well, we'll deal with the limits of integration in a second, but what we are left integrating is going to be e to the negative 2x. So you'll notice I did leave the limits of integration out. The limits of integration were from 0 to t, so let's plug those in right there for now. And we also notice that on this first term, we're going to have to evaluate that from 0 as well until t. Okay? So now let's take this one step further. We end up with the limit as t approaches infinity. We can deal with that first part right now, actually. So we have negative 1/2. We plug in t. We have e to the negative 2t. And then we subtract what we get when we plug in 0. But when we plug in 0, because of this x term right there, we're just going to get 0. So we can sort of leave that out. That's the first part. Now, we have a double negative right here. So that's fine. We end up with plus the antiderivative of e to the negative 2x from 0 to 2. So here it's going to be e to the negative 2x divided by negative 2, which we've already done. And then we're going to evaluate that one from 0 to t as well using FDC2. So fine. Let's plug that one in. We have limit as t approaches infinity, negative 1/2, and really we're just sort of rewriting all of this in. The minus 0 is gone. We have minus 1/2, which we can sort of take out at the start, and then we're going to have e to the negative 2t minus e to the 0, and e to the 0 is going to be 1. That's fine. And then we have to take here the limit as t approaches infinity, and we recognize that we have t's in here to do the limit of, and we also have this one to do the limit of as well. So if I take a look at this one first, what happens as t approaches infinity? Well, this whole thing is just going to approach e to the negative infinity, which you'll have to remember from Cal 1, that approaches 0. Okay, and so there's no problem with that one. However, when I go back to this one, we notice that there are two different functions making up this limit. This one we have just looked at. We know that it goes to 0. However, this one does not. This one approaches infinity, and so right now you're saying to yourself, yes, this is a problem. We have 0 multiplied by infinity. So what do we have to do? We have to go off. We have to do L'Hopital's rule. So here we can go off to the side, and we will come back to our integral later on. But for now, what is going to be our limit as t approaches infinity of just t multiplied by e to the negative 2t? Okay, and so for improper integrals, you're going to realize you do need to remember all of what you had seen before with L'Hopital's rule. Here with 0 multiplied by infinity, what do we do? Well, if it's 0 multiplied by infinity, we are going to convert this into one of the two indeterminate forms, either 0 over 0 or infinity over infinity. How do we do that? Well, all we do is algebraically sort of manipulate it. We choose one of these two functions and we artificially put them into the denominator. So in this case, it's pretty straightforward because one of them already essentially has a negative exponent. So it's just going to be t divided by e to the 2t. And now as t approaches infinity, we've gone from indeterminate form 0 times infinity to indeterminate form infinity over infinity. And so now, no problem, we can use L'Hopital's rule. And we get 1 in the numerator divided by e to the 2t. With a little bit of a chain rule, we multiply by 2. But that doesn't actually change anything. As t approaches infinity, this whole thing is just going to go to 1 over infinity. And so it's going to go to 0. Okay? So that whole part goes to 0. So coming back, we actually have, looking at this whole first term, that it does go to 0, but you do need to justify it using L'Hopital's rule. So now, let's put all of this together. We end up with 0 minus 1/2 times 0 minus 1. And so really, all we end up with is positive 1/2. And so what was the question asking for this one? We wanted to know ultimately, does the integral converge or diverge? And if it's convergent, find its value. Well, here we do have the value. The value is 1/2. And ultimately, our conclusion is that this one is convergent. And that's it. Another type 1 improper integral. Next time we'll take a look at type 2.